Okay, so something huge just happened in the world of computing. Google's quantum AI team just announced a breakthrough that isn't just another small step forward. No, this feels like a fundamental change in the game.
So what does this huge leap actually look like? Well, get this. They've developed a new quantum algorithm running on their Willow quantum chip that did a practical scientific job 13,000 times faster than the world's best supercomputers. I mean, think about that. A task that would take one of those supercomputers years to chew through was done in a matter of hours.
And this achievement marks the first time anyone has ever demonstrated what's called verifiable quantum advantage. Now, we've heard about quantum computers being fast before, right? But that word verifiable, that's the real game changer. It means we're not just getting some lightning-fast, weird answer from a quantum black box. We are getting a provably correct answer to a real-world scientific problem.
See, it's the combination of these three things that makes this so revolutionary. You've got the mind-blowing speed, you've got it being applied to a useful, practical problem, and you've got a result you can actually trust. You know, any one of those would be a big deal, but all three together, that's a true landmark moment in the history of computing.
So the big question is, how did they actually pull this off? Well, the secret sauce is this really clever new algorithm they came up with. It's called the quantum echoes algorithm. At its heart, this algorithm is really a tool. It's a way for us to peer into the incredibly complex, chaotic dance that's always happening in the quantum world. It's designed to measure how information spreads out or kind of smears across a quantum system. Think of it like watching the ripples spread out in a pond, but we're talking on an atomic scale here. The process itself is it's so elegant. So first, a signal gets sent forward through all the quantum bits, the qubits. Then, they give just one of those qubits a tiny, tiny nudge. And after that, they run the entire thing backwards in reverse. And out of all that seeming chaos, a tiny, crystal clear signal emerges, an echo. And thanks to quantum interference, that little echo gets amplified and it reveals all these hidden properties of the system. It's brilliant.
You know, Google's Sharina Chow put it perfectly. This isn't just a piece of code, it's a whole new scientific instrument, a quantum scope, or you could even think of it as a molecular ruler. It lets scientists measure things that were literally invisible to us before, like the precise structure of a molecule.
But here's the thing. To build a tool this powerful, you have to solve one of the biggest, most stubborn problems in all of quantum computing, the scaling problem. For decades, this has been the massive brick wall that researchers just keep running into.
So the old way of trying to build a quantum computer was monolithic, basically trying to build one single, giant, perfect unit. The problem is, as you add more and more qubits, the errors don't just add up. They compound, they explode exponentially, and the whole thing just becomes incredibly fragile. The new approach, though, is modular. You use smaller, interconnected, but separate modules. And this design keeps errors contained locally, which makes the whole system way more robust and way easier to scale up. And this analogy just illustrates the difference perfectly. A monolithic computer, it's like a giant sheet of glass. One tiny crack, and the whole thing shatters. But a modular computer is like a beautiful stained glass window. If one little piece cracks, who cares? The overall structure is still strong, still intact. It's just a fundamentally smarter, more resilient way to build.
Okay, so if a modular approach is the answer, what does that blueprint actually look like? How do you build a quantum computer that can actually scale piece by piece?
Right. This has always been the question for the engineers. How do we build these modules? And even more importantly, how do we connect them so they act like one single, incredibly powerful machine? The first piece of the puzzle is something called the qubit register. The best way to think of these is as super reliable, prefabricated building blocks, like perfect, individual Lego pieces. So instead of trying to build a giant, complicated thing all at once, you start with these stable, mini processor blocks, and then you just focus on linking them together.
Next, you need the right foundation to build on. The stage for this whole quantum performance is made of isotopically purified silicon-28. This stuff creates an unbelievably clean and quiet environment, which is crucial because it dramatically cuts down on all the background magnetic noise that can totally mess up delicate quantum information.
The analogy of a soundproofed studio is just perfect here, right? If you're trying to record a tiny whisper, you can't have a noisy air conditioner humming in the background. Silicon-28 is what gets rid of that hum, making sure the quantum signal comes through crystal clear.
And finally, we get to the most critical piece of all, the connection. They call this the electron bridge. It's an ultra-reliable, super-fast link that lets information and, this is key, quantum entanglement pass between the different modules. Entanglement is that weird, spooky connection where two particles act as one no matter how far apart they are. This bridge is what lets all these separate blocks work together like a single unified machine.
And when I say ultra-reliable, I really mean it. The fidelity of this connection, basically its accuracy, is over 99%. Now, that number might sound high, but trust me, in the quantum world, anything less than that is a total disaster.
That 99% number is what they call a make or break metric. Because think about it like building a skyscraper out of Legos. If every single brick is just 1% off kilter, that tiny error compounds with every single floor until the whole tower is leaning and just collapses. Hitting over 99% fidelity means every connection is nearly perfect, which lets them scale the quantum computer to incredible heights without it all falling apart.
So solving this massive engineering problem isn't the end of the story. Not even close. It's the beginning. It unlocks a future for quantum computing that, until now, was pretty much just theory. And the potential impact is just staggering.
And you can actually see where this breakthrough fits into Google's official hardware roadmap. They have now officially checked off the first two major milestones, proving a task that's beyond classical computers and building a working prototype with error correction. So what's next? The next great challenge, which they're working on right now, is creating a stable, long-lived logical qubit. And that's basically a super robust error-corrected quantum bit that's made out of a bunch of fragile physical ones. And this is where things get really exciting. The next big frontier isn't just about building better quantum computers on their own. It's about what happens when you marry the raw computational power of a chip like Willow with the reasoning power of an advanced AI like Gemini. You could create this incredible feedback loop where the AI helps design better quantum chips, and then those quantum chips supercharge the AI. It could lead to a complete explosion in scientific discovery. Which, of course, leads to a final, pretty provocative question. This combination of quantum and AI could unlock solutions to some of humanity's biggest challenges. We're talking clean energy, complex diseases, you name it. But an intelligence that's powerful enough to solve those problems might also be powerful enough to solve the problem of its own improvement. So, could this be the last technological revolution that we as humans actually invent ourselves before a super intelligent AI takes the lead? It is a profound thought, and with this breakthrough, we are officially one giant step closer to finding out the answer.